Okay, and let me go ahead and get started. So today we're going to focus on time series analysis. Um, so in our time series, it's somewhat different from the other statistical analyses that we've looked at. So I'm going to take some time to talk about what time series is. Then we're going to look at what's called smoothing functions. That obviously smooth the time series and how it appears. Then we're going to talk about interrupted time series, which is probably more useful in medical research. And then end up by talking about the concepts of cause and effect. So in time series analysis, this is different from the regular regression analyses, cross-sectional or repeated measures. And so usually time series occur at regular intervals, although to do the analysis, it doesn't have to. There are new developments in the software that can account for irregular intervals. The time series is mostly associated with econometrics. The Box-Jenkins reference is sort of the standard reference to the theory and behind time series analysis. So let me give you a couple examples here of time series analyses. Here's one from 10 or so years ago from the New York Stock Exchange. And so you can see that these are values of the stocks at different time points. And these can be days or months, but whatever, this is the typical time series in econometrics. And here's a more recent one. This is the Dow Jones, actually from about mid-2024 up to pretty close to today. And so there's a few things about this time series that is quite interesting. And let me point out a couple of them here. So one you can see is this big increase in the values. And this is, if you look at the dates down here, this looks like about November 5th or 6th, which of course was the election of last year. And so there was a big jump in the stock market, the Dow Jones values. And so as you can see, there are events that occur that may affect to a large degree the values in the stock market. Then there's a big decrease over here in around, looks like about Christmas time. Now what caused that, I'm not sure. But anyway, so you can see that there's fluctuations, and when it talks about the markets being volatile, that means that there's a large amount of change, either increasing or decreasing, and often those are tied to events, and could be world events, or in the case here of the election in November. So in time series data, the observations that we have are per unit time. And so it could be, as I mentioned, monthly, hourly, weekly, yearly. And the data are summary data. That is, it's like, for example, a monthly mean value. And the essential idea of time series analysis is that the value at any given time is a function of past values. Now, I say this is in contrast to, as I mentioned earlier, in contrast to our regular regression analyses that look at an event or an outcome as a function of, say, demographic values or clinical values. But in time series data, we're looking at any value as a function of past values. So this in this conceptual framework here, we need to talk about the concept of lags. And so, for example, here, if we have 10 units of time, whether they be months or years or whatever, we then look at the lag. So lag 1 would correlate time 1 with time 2, time 2 with time 3, 3 with 4, and so on. And then the second lag would correlate time 1 with time 3, time 2 with time 4, and then so on, as you can see here. And so the basic idea here is that observations closer in time are more highly correlated than observations further removed in time. And so the correlation between time 1 and time 2 you would expect it to be higher than, say, the correlation between time 1 and time 5, or time 2 and time 6, and so on. And we can plot the correlations over the lags, however many lags we have. And so you'll get a graph that'll look something like this, where we have the ACF, the autocorrelation function, what you call autocorrelation or serial correlation. Current values correlated with past values. And so we get this sort of oscillating kind of graph here as we look at correlations between the current values and the lags. And so in the lags that are closer to one another, we have higher correlations. Further out in time, they're less highly correlated. So we can look at different components of a time series. So we can look at trends, whether it's increasing or decreasing over time. If you remember the Dow Jones, basically from I think it was the mid 2024, there was a generally increasing trend over time. And even though there were different sort of ups and downs or fluctuations, that generally you had an increasing trend from July of 2024 up to the present. We can look at also what are called cycles. In other words, the series oscillates around a trend or a mean. In this case, a cycle is referred to as aperiodic. On the other hand, if we have a periodic cycle, then we talk about a seasonal trend. So for example, you can imagine if we had a time series of profits over a year, that there would probably be a seasonal cycle that would probably peak around Christmas time or slightly before that. And then just as we have error variance in regular regression, we have just random noise in time series. So those are the things that we'll look at in any particular time series to define the time series. So here's a couple of examples that are, well, fairly old, but as you can see in the figure on the left hand, where we have deaths in the UK attributed to bronchitis, that there's definitely appear to be seasonal trends. And then also you see that there's a time series for males and one for females, and it's obvious that the males are doing worse than females over time. And then on the right-hand side, this is pneumonia and flu mortalities from the, I think this is from the CDC from some years ago, but they have a time series that's in red, and then it's smoothed, and you can see the sort of the seasonal variation there. The lower smooth trend is seasonal baseline, and then the upper one is an epidemic threshold. So these are some real life examples of time series, as well as the Dow Jones average that we looked at earlier. So what we would like to do is we'd like to smooth the time series to get a model of the time series. And there's different ways of doing this. The primary one is what we call a moving average. So a moving average is a primary component of any time series. And I've given an example here of a 3-point moving average. So you have time 1 plus time 2 plus time 3 divided by 3. And so then the next value in our time series is time 2 plus time 3 plus time 4 divided by 3, and so on. Now we could do a moving average of 5 time points, or however many time points we want to look at. But then also we can smooth by just using regular regression that can be either linear, or most of the time it'll be nonlinear. So here's a couple of examples from 30-day readmission rates. And so the top one is what we call a LOWESS, or a locally weighted least squares regression smoother. The lower one is a nonlinear smoother. And so you can see the difference in the two, where using the locally weighted least squares regression results in a fairly smooth trend line, but of course, it doesn't always capture the particular fluctuations, whereas in the nonlinear one, you can see that it comes closer to actually capturing the fluctuations in the time series. And so particularly you can see out at the end in January to July of 2014, we have a big increase and a decrease, which is reflected in the nonlinear smoother, but not in the lowest regression smoother. So time series models, as I mentioned, the primary components of a time series model is the autoregressive part, the serial correlation or the autocorrelation, and then a moving average part. And so we refer to this as an ARMA, or an ARMA model. Point to remember is that time series must be stationary before estimating an ARMA model. What that means is that the probability distribution of the series does not depend on time, which of course, in just looking at the time series, that's not going to be the case. So if we have an ARMA model and we designate that with the letters P and Q, where P represents the autoregressive component and Q the moving average component. And so then we will solve for values for P and Q. We can also have what's called an ARIMA or RIMA model, where in addition to the autoregressive and the moving average parts, we have what's called an integrated part. And we designate that by D, which stands for differencing. In other words, in addition to considering the autocorrelations or correlations in a moving average, we're going to, at any particular time point, we're going to subtract the previous time point. And so here's an example of a time series of IBM stock prices over a certain period of time. And so you can see that there's sort of minor fluctuations, and then there's a big decrease at around day 260 or 250 or 60 or so. And so we might want to, obviously we'd want to know why that occurred. But what we need to do before we define this or model this time series, we need to difference it. And so it needs to, when we difference it, the time series will look something like this, where what's called white noise, where it's serially correlated and it's a random variable with the zero mean. So when we go to model our time series, we'll do this sort of differencing to get white noise, or to get to the point where we have white noise. That is, we have taken out the trends. So as I mentioned, the time series is, because it's solely looking at present values as functions of past values, it actually it has application more in economic sorts of context rather than in medicine. However, one application of it that's often used in medicine is what we call an interrupted time series. And generally, this is where we want to look at the impact of some intervention on some outcome where we have a time series of outcome. Now, this can be analyzed as a time series, but more typically, it's analyzed as a regression, just continuity. And what I mean by this is that we use ordinary regression to model the time series before the intervention, and then we use regression to model the series after the intervention. And so if our trends turn out to be linear, then it's really easy, because then all we need to do is either compare the regression slopes or compare the regression intercepts before and after the intervention. And so here's kind of an example of what we're talking about here. So here we have A1C values before some intervention, and then A1C values after some intervention. And so we can get a trend line both before and after. We can see that the trend is really flat. There's actually no trend at all between the two, but we can see that there's a difference in the overall mean before and after the intervention. So in this case, that we would say that our intervention worked in lowering A1C. So here's a graph where our conclusion would be obvious. We would say that in this case, there's no effect of the intervention, because the whatever our outcome is decreasing at a constant rate before the intervention, and after the intervention, it's decreasing at the same rate. So we could conclude that our intervention had no effect in this case. We might get something like this where there is an effect, but then the effect dies out over time. And we'll look at a couple more of these later on. So I want to give an example here where we did interrupted time series, where we had the impact of I forget what BRIDGES stands for, but anyway, there was a care management program that was implemented, and we wanted to look at that on 30-day readmission rates. And I believe this was for percutaneous coronary intervention patients, PCI patients. So one of the, of course, things that we might want to ask, and what we could ask is, if we did just a regular regression analysis, are there demographic variables or clinical variables that affect the 30-day readmission rate? And so we do just an ordinary regression analysis. But if we have a time series here, then we can look at other factors that might cause our outcome. And we refer to this as Granger causality. And what we're saying here is, does one time series lead or cause another time series? And so what we asked here is 30-day readmission in a function of length of stay in the hospital? Is it a function of comorbidities, or is it a function of having congestive heart failure? And so just remember that in time series, all we're doing is developing a model where present values are solely dependent on past values of the time series. But here we've got two time series, 30-day readmission rates, and then length of stay or comorbidity counts over our time period. And so we're going to look at the effect of one time series on another. So here's an example, or here is the data for from I think it was 2010 to 2014 of the readmission rates. So we have monthly readmission rates here. And so here is a plot of those values, and this is our time series from 2010 to the midway through 2014. And so you can see that just by looking at this, you know, there's a lot of fluctuation. And so we might want to use time series to see if there's any trend. And then also we're going to look at other time series like length of stay and comorbidity counts to see if those cause the readmission rates. So if we were to do a test for white noise, we would see that the current time series as is not is not just white noise. It's there's differences in the distribution over time. And then this is just a picture of the autocorrelations over the different lags. So in doing the analysis, and this is actually from Stata output, but it would be similar in any other statistical package. So what we're going to do here is look at 30-day readmissions, and we're going to suggest two different components here. There's an ARMA component where we have autoregressive and the moving average, but we've left out the differencing or the integrated part. And then we've also included here a seasonal component, which is the same where we have the autocorrelation and the moving average part, and then we're going to say that there's a 12-month cycle to this. And so here's our output in terms of that looks similar to regression output, where our regression coefficient here is the, the mean of the time series. And so here's the test for our autoregressive component, which is not statistically significant, and our moving average component, which is. And then we also look at our 12-month cycle here and see that our autoregressive part is statistically significant, but so is the moving average part. And so you're going to ask, how do we know which one, which one is correct here? And so we're going to do several models here. And so here is the one without the seasonal component. You see here that we have the same mean of the time series. And here now we have the autoregressive. We take out the seasonal component, the autoregressive part of the model is statistically significant, as is the moving average. And so here's another model then where we've taken out the autoregressive part and just included the moving average part. And again, that's statistically significant. So now we've got three different models here. And then here's another, a final one, I think, where we just include the autoregressive and we take out the moving average part. So how do we know which model to use? Well, we use our information criteria to decide which model is the best model. And so in the case of the information criteria, whether it's Akaikis or Bayesian, we want the smallest value possible. And so we see that the smallest value is for the moving average and having the time series as well as the seasonal, 12-month seasonal time series in there. Now that's not much different from the one where we include the autoregressive. So the choice between models is probably going to be one of these two because they're clearly smaller than the information criteria for the other models. And so you can see that in this case, including the seasonal aspect of the time series is probably is necessary to include. So in choosing a model, that's how we choose models, is looking at the information criteria. So here is our 30-day readmission rate. So we have the observed time series and then overlaid with our different models. And so here's the one where we have just the moving average model overlaid. And then even though that's not our best fitting model, we can see that now we have our test for white noise is not significant, is which we want. So that model will be statistically significant, but also if we had our seasonal average model in there, that would actually be a better fitting model. Okay, as I alluded to before, we can also look at the change after the intervention compared to the after the intervention compared to before the intervention, and we can look at different patterns of change. And so I'm not going to do this, but we could also do a test for whether the change is gradual and then permanent or temporary, or whether the change is abrupt and permanent or temporary, which is a little more complicated to do, but we could do that. So here, we now then what we do is when we look at our intervention, our Bridges intervention, our care management intervention. And so that occurred about April of 2013. So we have the time series before April of 2013, and then we have series after April of 2013. And so what we want to do then is we want to ask the question is there an effect of the intervention, which I've labeled as Bridges up here, and you can see I have the model where we have the moving average, and then for the seasonal, I have both the autocorrelation and the moving average. And so now we can see that our test for our intervention here is statistically significant. And we can see that the coefficient is negative, so that means that there was a decrease, however small, in readmission rates after the intervention. And then the rest of this is just the test for the moving average, or the autocorrelation part of our time series model. So in terms of asking whether we have Granger causality between two different time series, remember we just looked at this at the time series of admission rates before and after our intervention. So now we want to ask, is there a time series model that we can say causes the outcome model, or is the in a sense the what we're looking at as a cause, is that actually caused by our primary time series model? In other words, X sub t causes Y sub t. And so in terms of how we do this, then what we're saying is if the past values of our I guess we could say our information that we want to look at is causing the outcome, in addition to the information in the past outcome values to predict future Y, we say then X Granger causes Y. And note there that we're not saying that Granger causality may or may not indicate true causal effect. But Granger causality is, as we say in mathematics, a necessary but not sufficient condition for true causality. So this is, in a sense, kind of looking at regression equations as we normally think of them between two time series, but we can get at whether one actually causes the other or not. And so in terms of the causality test, if Y sub t model as a function of x sub t is significant, and the x sub t as modeled as a function of the y sub t, that is the outcome that we're really interested in, is not significant, then we can say that x causes, or Granger causes, y. If it turns out that the opposite is true, that y sub t is not is modeled by x sub t is not significant, but the opposite is, then we can't say that x causes y. If, on the other hand, both are statistically significant, then we really don't know what to say. We have no conclusion that we can make. So here's then an example from our 30-day readmissions looking at comorbidity. And so what I've plotted here is the readmission rate as before, and then overlaid on that is the comorbidities count. This is the Alexhauser comorbidity count. And so we have another time series that's of comorbidity counts that you can see is plotted on the right side here in terms of those counts. And so what we're asking is, does comorbidity cause, or Granger cause, readmission rates? So here's the same thing for congestive heart failure. We would plot our time series for readmissions and our time series for whether a person has, or in this case, what we would be plotting would be the proportion of patients at any time point that have congestive heart failure. So when we do our tests then, we first of all then want to look at readmission as a function of congestive heart failure, readmission as a function of comorbidities, and then we're also looking at readmission as a function of previous hospitals. And so, and then finally, we look at readmission as a function of all three of those. And so we can see that congestive heart failure and comorbidity just by themselves are statistically significant. Previous hospitalization is not, but if we can put all three of them in the same equation, then it is statistically significant. So we have at least our cause here being correctly related to the outcome. Then we also want to test, well, is, for example, congestive heart failure a function of readmission? Is comorbidity a function of readmission? In other words, we're turning the equations around. And so we see that in each of those cases, it's not statistically significant. So we can conclude then that congestive heart failure and comorbidity are Granger causing readmission. And then if we put all three in the equation together, we can say that all three of these would be Granger causing readmission. And again, what we could conclude then is that at least in the right direction, we have at least part of a cause and effect here in that these variables, congestive heart failure, comorbidity, and previous hospitalizations are causing, or more accurately, Granger causing readmission, which is sort of what we would expect. Whereas if we just do regular regression, then we can't really say anything about cause and effect. Okay, then another use of time series is when we want to do what's called bivariate time series analysis. where we cross-correlate two time series, again, to get at cause and effect. And so I have the sort of formulas here, but basically what we're saying is that the correlation at any lag or lead that represented by the K is a function of the correlation at the two time points here for the two time series divided by the square root of the variance of each series. And so K, as we talked about before, represents lags, but now we're also going to talk about leads. In other words, K here can be either positive or negative, and we'll see what that means here with an example. So if the peak in correlation of the autocorrelation series appears on the plus side of K, then we can say that X leads Y, or in our causation, that we can say that X causes, again, as a necessary but not sufficient condition. So if this is the case, if this is true, then the correlations on the negative side for the negative lag should be statistically zero. And so I have an example here that I did quite some time ago. Actually, I use this because this is the only time I've done this where it actually worked or made sense. But anyway, so the study wanted to evaluate the degree of heterogeneity within a population of spinal neurons known to elicit urinary bladder contractions. And so the hypothesis here that homogeneity would indicate a single function for these neurons, whereas heterogeneity would indicate subgroups of neurons with multiple functions. And so we used bivariate time series analysis here to evaluate heterogeneity of three populations of spinal neurons. And these are designated numerically with respect to their effect on bladder contractions. And so differences then were assessed by examining the cross-correlation functions of the neuron groups with respect to peak correlations and the lag at which peaks occurred. And so this is what the data actually looks like. So you see you're getting pressures here at various times, although they're occurring within just a few seconds of each other. And then we have three different neuron groups here, designated 1, 7, or 10. And so here's just the time series for one, in other words, number 1 overlaid with number 10. And then this is number 7 overlaid with number 10. But what we're interested in then is the cross correlations. And so what we do when we graph this, then we see that what we get is that in terms of the groups of neurons, that they have a positive peak around the early positive lags from 0 to 1 to 5, where we have positive correlations. And then before in negative lags, we have negative or non-significant correlations. And so what we're concluding in this study then is that these groups of neurons here are are similar. That is, they all peak at approximately the same time. So again, what we're saying is that in time series analysis, and as far as medical research is concerned, is that it's primarily best in assessing intervention or implementation, where you have data before and after some particular intervention. So for example, we did readmission rates as an example. You could do discharge rates or infection rates, hospital infection rates. And as I mentioned before, these are usually analyzed by regression discontinuity, but we could analyze these as time series and compare the two time series functions before and after. Time series forecasting, because that's what is typically done in econometrics, is being able to predict future values of stocks or whatever you might be interested in. As far as forecasting patient outcomes, that's not particularly useful. It's not very accurate. And then the other use in medical research is assessing causality of two or more time series. And here we're talking about Granger causality, or does one series lead or lag the other? And so by doing this sort of analysis, bivariate time series analysis, we can get more of an indication of cause and effect than we can by just doing ordinary regression, because that's ordinary regression does not get at causality. But by using time series, we can at least see if we have a condition, a necessary condition for causality, although it's not a sufficient condition. So in terms of time series analysis, I guess the basic conclusion that we want to say is that it probably has limited use in medical research, but there are a couple of instances where we would want to, where we might apply that, and where it has been applied in doing intervention, assessing the impact of interventions or implementations of programs. Okay, so I want to thank you for your time. We have a few minutes here if there are any questions. I think let's see, I think use the chat, I guess, for any questions. If if not, we can want to again thank you for your time and attention, and then we will see you next month, February 21st, I believe it is. I'll stay on a few minutes if someone thinks of more questions. Oh, okay. So there was a question: will these slides be shared? Yes, I send these to the folks at Georgetown, and then they send them to the people who have registered, along with the I think it's a YouTube link that you can review the presentation as well as the slides. And then also, let me go down here to, if you want to have any further questions or want to follow up, you can contact me at my MedStar address here. Okay, so a second question was, could you describe how the frequency of sampling can be accounted for in time series analysis if individuals in a study have different frequencies of sampling? Can values be interpolated in a meaningful way? Well, as in time series, we have to have individuals, or we have to have values at a particular point in time. As I mentioned before, this is typically, regular intervals. So if you have patients who have been sampled at different times, then what you would have to do is consolidate those into a particular time frame. So maybe you want to have your your first time series point would be patient responses from, say, within 3 to 5 months, or 3 to 6 months, or within a 2-month period, or however you do that. So you would have to group those together in for one particular point in the time series. And I might add too that that's one of the advantages of time series analysis, is that you don't have to worry about missing data. That's not going to affect the analysis. So if you have sort of mean values at a one time point, that can be based on different numbers than at the next time point, because what you're analyzing are the mean values, or the total counts, or the mean counts, or whatever you're particularly interested in. Okay, if there are no more questions, then I want to thank you for your time and attention, and we will see you again next month.